Hello everybody. Today we will be discussing about a few aspects of Lagrangian mechanics. Okay, so let us start. So what have we discussed so far? We said that we can cast our mechanical problem in the following way. We know the configuration of the system at a time t1 and the configurations, let us call them q1. So q1 is essentially I'm writing it for all the different queues. So I know all the different queues at the time t1. So that's all the different queues are denoted by q1 here. Similarly here t2, and I know all the different queues. So I know the configuration of the system at t equals to t1 and t equals to t2. Absolutely. I am asking the question now that what will be the trajectories of the system, or what will be the set of configurations at all times between T1 and T2, and what the system will eventually follow. Let me denote that by this line. Okay. Now I am supposed to figure that out. So what I do, I say that first of all I define a function which I call the Lagrangian function, which is given by all q's. So let me write it as qi, and when I say given by all qi's, it's obviously is a function of time. They are function of time, so that is the trajectory. And it can also depend on time in general. So this is specific to the system. Right? Now what do I do? What I do is the following. I calculate this. Now before I writing that, let me again tell you what this function is. This function has to be, is a function, L is a function of three things. One is of course time, and the others are how does q changes with time and how does q dot changes with time. Which means to calculate this function between t1 and to calculate this function, I need to know a path in this configuration space over which I will calculate my function L. Okay, so this is any path. I can do it for any path. So if I choose q as a function of t, qi, all qi as a function of t, and qi dot, all qi dot as a function of t, then I know what is my L. Okay, and then what I do for that particular path, I calculate, and I'm not always writing the time dependence explicitly. I calculate this, and this I call the action. And we look at now what will this depend on? Depends on the path, right? So let me go back once again and remind you that I have written down the Lagrangian, the functional form of L about qi and qi dot and t depend on which system I am working with. So that is fixed. We'll say choose the system. But that still doesn't choose what is the value of L, because for different trajectories for the given system, L can be different. So I choose a trajectory and then calculate this integral. Okay, and so which means that this S depends on which path I have chosen. So then what do? We look for delta S equals 0. So if I know when is my delta S equals to 0, that will give me the trajectory. And that is essentially my Hamilton's principle. So just like for the D'Alembert's principle, we are exploring all the nearby points where delta W prime was going to be 0. Here we are exploring all the paths. So I cannot only do it for one path and then I will find it. So I have to do it for all the possible paths. And then when I will hit that particular path, which is the actual trajectory. So this is the actual trajectory. What do I mean by the actual trajectory? I mean that if these are the points where the system is at T1 and T2, and if the system is following a particular Lagrangian form, then this is the path that the trajectory will follow that the system will follow between T1 and T2. So that's what I mean by actual trajectory. And when I calculate the action in all the paths, it will change least when I go out of the actual trajectory. So that's why also it is called a least action principle. Now this is not the only least action principle. There are other least action principles also, but mostly we will talk about only this principle. You can learn about the others and we can discuss later. But this is the Hamilton's principle, which is one of the least action principles which we have talked about. And using this, we found that the equations of motions can be written this way. Remember that we also said that we can write down the Lagrangian with any choice of coordinate. The way Hamilton's principle describes it is not required that it has to be in the generalized coordinates, though I have written in terms of q, but it will be true for any type of coordinates. It can be worked out. Okay, so I said the equations of motion, and those equations of motion, which are the Euler-Lagrange equations of motion, that depends on how many coordinates you have used to write down the Lagrangian. So let me be a little bit more specific at this stage, that when I wrote down that the Lagrangian is a function of qi dot and t, if I have n q's, so if I have n q's, so I'm working with the n-dimensional coordinate system. I have n of qi's here, n of qi's here, and one time here. So the Lagrangian is actually a function of, can be a function of 2n plus 1 variables. Okay, and out of those I get n equations. So these are the n differential equations. And they are of second order, n second order differential equation. So I will need 2n initial conditions to solve them. Okay, this we have learned last time. So these are called the Euler-Lagrange equations of motion. Right? Now you see, in the case of D'Alembert's principle, we had the delta W equals 0, and we wrote it with a delta because that work done corresponds to a virtual displacement. So here I write delta for what we call the variation of the path. If you think about it a little bit, and if you go through the previous lecture once more after hearing what I'm going to tell you now, you can convince yourself that these variations of different paths actually are the virtual displacements that we were talking about earlier. They are equivalent. The only difference is that here we are looking at the variation over the entire path, and there we were looking at the variation at each instant of the path. Okay, so that's the only difference. Otherwise, they're actually the same thing. Okay, so this is what we learned last time mostly. So let us proceed forward with this amount of knowledge. And let us take a particular case of the Lagrangian. So before we go further, let me put this in bracket because this is something that we may need quite a bit. And let me also keep this in bracket, which is defining the Lagrangian function, which is a function n of nqi. I'm sorry, nqi, nqi dot, and t. And let me also remind you that, not remind you, rather let me also tell you about some convention. It's called the Summation Convention, and it may be useful for us. So what is the Summation Convention? It was devised by Einstein because he had to work with a lot of such summations in the general relativity. The Summation Convention tells you that, say I have to sum over something, and then say I have to sum over two things which are like a and d, and I have to sum over 1 to n. And here what all I am doing is I am multiplying the ith component of a with the ith component of d, and then adding all for all I. So he proposed that this can be equivalently written as, just you don't write the summation, just write this like this. So if an index is repeated, it is summed over. So this is our understanding. So this is our convention. So the summation convention is that if any index is repeated, you just assume that it is already summed over. So you don't need to write the summation symbol here anymore. You don't write it. Okay, so that is Einstein's summation convention, and we may be using it in some of the discussions today. So that's why I wanted to introduce it to you. Okay, special case. Lagrangian does not depend on time explicitly. Which means L just depends on qi dot and no t. So I am writing t and then cross it out. Okay. So we want to look at that special case. Now in general, how do I write? So if I have L, so dl dt, what will be dl dt? Now this is a total derivative, right? So this is total derivative. Which means how does n changes with time? Now that may be just because L is explicitly dependent on time, so I can have a change of L with respect to time like this, and then I should write dt dt over here, but that is is 1, so that is just 1, and then I will have to write all the other, so del L del L del Qi, then I get dqi dt. But you see that dqi dt is nothing but qi dot, so I can replace that with qi dot. So this is nothing but qi dot. This is nothing but qi dot. So I can just replace it with qi dot. So let me do that. And then I will have the variation with respect to dqi dot, and let me keep this as dqi dot dt. If it is a generalized coordinates, dqi dot dt alone is not the acceleration. Because of that, I did not write it qi double dot. I can write that, but it may give you a wrong impression. So that's why I avoided it. But this is the case. So this is always true. So this equation, this is always true. In fact, this is the definition of del L del T if L is a function of these three variables, right? It doesn't matter which system you are looking at. It even doesn't care about which trajectories you are looking at. Okay. Now, if I am on the trajectory of the particle, so along the trajectory followed by the particle, so how do I get the trajectory followed by the particle? Well, I get it from the Euler-Lagrange equation, right? So the Euler-Lagrange equation must be true for the trajectory followed by the particle. And that depends on now which system you are looking at, etc. I mean, the trajectory depends on which system you are looking at. Well, one thing I have done here, if you have not noticed, that I have not put a summation sign over here because I have both I index in two of these, so that essentially means it is repeated. Otherwise, I should have put a summation sign, but I have already used the Einstein summation convention. I'm sorry. So there is no qi dot over there. So this is equals to 0. So this is Euler-Lagrange equation. And I can also write it, you will not quarrel with me if I write it this way. This is only true along the trajectory of the particle. You will not kill me if I say that I don't know the trajectory at this point, but I know that this will still be true along the trajectory of the particle. Now, if you look at the previous expression, you have del L del Qi. You have del L del Qi over there, so I can just replace this with that. And if I do that, then what do I get? I get dl dt equals del L del T plus, so this is ddt of del L del Qi dot and then Qi dot, and then the next term is del L del Qi dot and ddt of Qi dot, right? Now you see something interesting has happened. If I look at these two terms, ddt of this keeping that fixed and then keeping the first term fixed and ddt of that, which means these two terms I can write together as ddt of del L del Qi dot Qi dot, right? And let me do a little bit of rearrangement here. Let me bring this del L del T in this side, so this becomes minus ddt of L essentially, and let me put this in the left hand side, says that this becomes minus del L del T. And then you can write this as del L del T minus del L del T equals ddt of del L del Qi dot Qi dot. Sorry, so I just want to keep the L also in the same time derivative. Okay, so this is true in general along the trajectory. So this is true in general And this is a remarkable equation. This left hand side you have partial derivative, in the right hand side you have total derivative. Which means the left hand side is the explicit dependence of time on L, right hand side is the total dependence of time with respect to total derivative of time of this entire quantity. Right? Now if I have, if Lagrangian is, if L does not depend on time explicitly, if L does not depend on time explicitly, so what is the mathematical statement for that? That is essentially del L del T equals 0, right? Which means that ddt of this entire thing becomes 0, and which means that I can write del L del Qi dot minus L is a constant. It's a constant of time. So let me write the statement here clearly. This is true along the trajectory when Lagrangian doesn't depend on time explicitly, that is del L del T equals 0. C is independent of time. Right? Now this result has a name. It is called this Beltrami identity. Okay. Now we already know, so if I have to define a momentum, see, so far we have not talked about momentum at all. It did not come into our picture. If I am using Newton's laws, the Newton's second law is talking about the rate of change of momentum. Here, so far we have not talked about momentum at all. But if I have to define a momentum, one way is the following. So for each Qi, the corresponding canonical momentum is called Pi, and this is calculated by del L del Qi dot. This is the definition. Okay, so this is the definition. You cannot ask why it is so. This is how a canonical momentum. So this is a canonical momentum, and there can be momentum defined many other ways, but this is the canonical momentum, and it is defined this way. Okay, which means that this previous equation you can write as Pi, and you see that I again have I repeated, which means that it is summed over. So this is equals to constant, and later you will see that this constant in this particular case is nothing but the energy. So this you will see when you learn the Hamiltonian mechanics. Okay, so we understood one thing here now, that if the Lagrangian doesn't depend on time explicitly, then along the trajectory there is something of the system that does not change, and that something of the system is defined in terms of the Lagrangian this way. Okay, so that we have understood. And this is a big result, because if this something does not change along the trajectory, maybe I'll be able to use this something to find the trajectory. Okay, and when you'll go to the example of the central force, we will see how that works out. Okay, so this is so far so good. This is about one property of a particular type of Lagrangian, and I also defined as a pass, I also defined the canonical momentum for you. And we'll come back to the canonical momentum later, but before that, let us look at what we are doing here mathematically. So if you look at carefully, what we have done is equivalent to the following case. So I have a function, say capital F. It is a function of variable y. The y depends on x explicitly. It's also a function of y prime, which is nothing but dy dx, and it can also depend on x. And what all I am doing is I am summing it over, or integrating it over all x between x1 and x2, and defining that with the action. Now, given a function, given how y depends on x, I have a value for s, right? And I can vary now function yx, and as I vary the function yx, I can seek for extrema of x of s, sorry. So this type of problem has a name. It's called the calculus of variation. Okay. And it is not only used in classical mechanics in the form that I have shown you, it is used in many other cases. So let me give you at least a couple of examples. And one example, and I think that I will not work out either of the examples, and that will be your homework to work out the examples completely. And then for the first example, so let me tell you the example and then tell you why I am telling you about it. So this is a completely different problem. The problem is the following. So I have a beach, a sea beach, where a lot of people are playing around, swimming, and there are coast guards in the beach. Okay, so let me draw a sea beach. So this is a line between the sea and the sand part of the beach. So you have water here. So this is the part water. Okay, and in this side is sand. This is sand. Okay. Now there are coast guards, and their job is to ensure the safety of the tourists. And it turns out that there is one tourist here who is drowning, and he is shouting for help. So let me make the tourist colorful. He's drowning and shouting for help. And that was listened by a coast guard who is stationary here. Okay. So what he has to do? He has to go and save the tourist. So that's his job. That's a part of his job. So what will he do? That is the question. Now, In the sand part, if he walks, he will try to walk in straight line. That is obviously, or even if he runs, because then he has a chance to reach that person who is drowning faster, and you want to reach him faster because otherwise there is the best chance that he can save that person, right? Fine. So when he runs in the sand, he has a velocity, say vw, v sand, vs, and let me define this distance as ls. Then similarly, this distance I call, say, L water. And when he runs in the water, well, he doesn't run in the water. That person is drowning, means it's quite deep into the water, must be. So this, he swims in the water, and that speed is V water. Now the question is, what is the path that he will follow? So will he follow this path? Now, see, if we follow this path, okay, so let us start from an extreme path. Say he follow this path. Okay. Now, for this path is very good because he spends most of the time in the sand where the speed is less, and then goes a little bit in the water where the speed is, okay, sorry, the speed in the sand is obviously higher, so he spends most of the time where he can run at the fastest speed, and then he goes to the water, there he spends less amount of time. He must be very clever. But you realize then that he has to spend a lot of time here, so maybe he will try to minimize that by going this way. So he spend equal amount of, according to this figure, equal amount of distance in both sand and water, and then maybe he will be able to maximize this. But somebody may also try to go like this, where which doesn't look very good, because though you spend very less amount of time in the sand, you spend a lot of time in the water, which where your speed is less, so it's not supposed to be good. So the question is that what path he should follow if he knows physics and mathematics, etc. How do I figure it out? To figure it out, so let us see that what we have to do. So that person has to go from one point to the other. Let us name those points. So let me choose the origin here, such that this point now I can label as 0 minus ls. Okay, and this point is then labeled as, so maybe he is at x0 and lw. Okay, so let me call this as point 1 and call this as point 2. So what he has to do is to minimize the time, and the time is given by point 1 to point 2, and if infinitesimal displacement is time step is dt, so this is p1 to p2 dt, right? But that is not written in terms of any of these variables, so how do I write it? Well, you will say that, well, dt I can write as distance, obviously infinitesimal distance, by velocity, and that must be instantaneous velocity, because I am talking about a differential change in time. What is the velocity at that time? That is what will matter, right? Nice. So can we calculate this out? Well, here I can call this, say, x-axis, and that's why I have written x0 over there. So call this, say, y-axis. So if it is so, then I can write the instantaneous distance ds as dx square plus dy square, square root of that, and that I can take dx outside, and this just becomes 1 plus y prime, the function of x, to the power half dx. Then what I can do is I can break this integral. So I can say, well, I don't know exactly what path he will follow, but I can say that, okay, so he goes up to a point x in sand, and then he goes into the water. So I break this integral into two pieces. One is from P1 to that point. So let's call this intermediate point as P small I. And then, so this is all about water, all about sand. And then Pi to P2. And dt I can now replace as ds. So this is essentially ds and by velocity. So the first will be the velocity in sand, and in the numerator you will have ds, which we have calculated just above. So this is dx, and x goes from 0 to xi. And then I have to add the water part, which will now go from xi to x0, 1 plus y prime x to the power half, but now divided by v water. You see, the velocities were supposed to be instantaneous, but the velocities we have assumed doesn't change while he is in sand or while he is in water. So those are constants which may come out of this integral. But what does the result of this integral depend on? It depends on xi, because everything else is known. Xi is something unknown, so it will depend on xi. And you can see that here the xi decides which path the particle, the coast guard will take, right? If I now look at this integral, what does the integrals depend on? Integrands. Integrand depend on y prime, right? So in general, if you look at these, this has the form x1 to x2 L y prime x dx. In this particular case, it is only a function of y prime, but it has this form. Okay. So what I ask you to do now, first figure out what you will write for y prime, and then put that over there. See, okay, let me give you a hint what you will write for y prime. See, y prime is the derivative, right? So y prime is essentially dy by dx, which is nothing but the slope of the path at that particular point. So if I am in the water, y prime is the slope of this line essentially, and that is simply this LW divided by x minus x naught. So that's what you have to replace y prime for in the water region, and then similarly you can replace the y prime in the sand region. Once you do that, you can do the integrals now. You get txi, and then you do the variation with respect to xi, and you'll find out for what xi, what is the value of xi for which txi is minimum. That will be the coast guard's trajectory. The coast guard is educated enough, right? Please do that, and once you do that, you may find something which is so interesting, and then you will realize that where this problem comes from. And where this problem comes from, if you realize that, then you will realize that this is a principle of least time instead of action. That is being used in that particular area of physics. Okay, so that is one example we talked about. Let us talk about another example which comes from mechanics. So it's quite from our home right now. This is also an example of principle of least time. So what is the example? The example is the following. So let me again draw the axis such that it becomes easier for us later on. And when I'm drawing this I'm assuming that all the motions are happening in 2 dimension. You can do it in 3 dimension also, but 2 dimension suffices for this motion. Why, that we'll learn again in a week from now. So that's the origin of my coordinate system. Now I call this y, we call this x. This is obviously the negative y-axis. That y only means that it's the y-axis. And then I have gravity, which pulls downwards. So there is a gravitational force downwards. Okay. What you have to do, a particle is in this position initially, and the particle will eventually come here. It has to come here, P2, which I can denote as x naught minus y naught, minus because it's below P1. It has to come this way under the influence of gravity. So the question is, so the particle has to come, the particle has to come to P2 from P1 in least amount of time. You see, it's a principle of least time. So this has a name. The name is called Brachy-Strokone problem. Chron means time, and I cannot break out the rest of it for you because I don't know how this German name works, but it's essentially telling you what is the path for the shortest time. So it can be like this, it can be like this straight line, if you think it can be like that, it can even be like this. So which one? That is a question. And if you start thinking about it, you will again have the same dilemma, because you may think that it follows a straight line, but then you will realize that it is not using up the gravitational force. So it may be that it is easy to come here by using the gravitational force and then go this way. So there can be many such possibilities which you can think of. But how do I solve this problem? Using the calculus of variation. But how do I solve this problem? Using the calculus of variation that we have just learned. So again, this is a problem of principle of least time. So I start by defining the time equals, and this then I have to go from P1 to P2 and then dt. And this we had actually worked out already. So this is P1 to P2, infinitesimal distance. This is just from the previous problem or example, by instantaneous velocity. And now, what is the infinitesimal distance? Well, that we worked out here. It comes out to be this, ds equals that. So I just write that down. I'm sorry. So this, there is a dy squared there, so all these will come with a square, which I forgot. I just realized now. Okay, now what do I do? Well, I can now say that, well, in this problem, if I look at this point, what is the the value of this C which we discussed here, this C. Okay. What is C? Well, as we know already, as I told you as a past time, that this C is nothing but the energy. C is the energy. Then I can write that as half mv squared minus gy, and this is the constant energy, right? Now you see, gy is the potential energy. I can choose it in such a way that the potential energy, I can choose the potential energy in such a way. See, I am free to choose the zero of the potential energy in kinetic, in classical mechanics. I can choose whatever I call zero of the potential energy. That is, I have free choice. I don't have that free choice in the quantum mechanics, as you know that there are 0 points energies in quantum mechanics. But classical mechanics, I can always choose zero of the potential energy. So I choose the potential energy such that at P1, that C is equals to 0. And if it is so, then I get half mv squared is G times Y. And that gives me V as this is a constant, and then I have root over of Y. So my total time becomes now, see, this integral is, I forgot to write the integrand, which is dx, is from x1 to x2, or what did we call it? So 0 to x0. So this is 0 to x0. These points are fixed. So I have dx over here. I can take that. Okay, so let me go back a little bit. So this is equals root over of 2g by m. Okay, so let us calculate the time taken, which is an integral from x1 to x1 is 0. So integral from 0 to x0. So this point is P1 is at 0 and P2 it is x0. And then I have in the numerator 1 plus y prime square to the power half. In the denominator I have v, and the v I can take this constant terms outside, m by 2g, and what remains is root over of y, and I have to integrate over x. Right? And you see again, I have come up with a case. I can just compare this with x1 to x2. This is a variational problem, y prime x dx. And you directly read off the Lagrangian, which is a function of y prime and x, in this case is nothing but root over of m by 2g 1 plus y prime square to the power half by root y, right? So this is the Lagrangian, and if you have not noticed already, it is independent of x. Okay, that actually we have already used. Well, you have not used that. Okay, so I have not used that. We have used the fact that the system is a conservative force gravity. Because of that, this comes about. Now we are saying that Lagrangian is independent of x. There is no explicit dependent of x in this, which means now I can use Bernoulli identity, or I can just write down the Euler-Lagrange equation for this. What will be the Euler-Lagrange equation for this, by the way? So it will be d dx of del L del y prime minus del L del y equals 0. And that is essentially, if I solve this equation, I will get y as a function of x. So this will give me y as a function of x. And that's what we wanted. What is y as a function of x? That is the curve. That is this curve. This curve is y as a function of x. Okay. So I will not solve it for you. It will take quite some time to solve it here in a discussion. So I will leave it for you to solve that. So that is your second homework today. Okay. So this completes the two examples we promised to talk about. There are many other examples, so which one can talk about, but this is what we will do in this lecture. Okay. So now let us switch topics a little bit, and let us come to a particular case of something which has a lot of name. So let me write the names. Okay. The name usually we say doesn't matter, but I just want to put the names because each name has a meaning, and I will tell you some of them at least. So what is it? Well, this we have talked about canonical momentum. So what is a canonical momentum? Corresponding to each coordinate qi, the corresponding canonical momentum pi is defined as del L del qi dot. So that we have talked about. Right? Now, remember what Lagrangian is a function of? Lagrangian is a function of nqi's, nqi dots, and time. Right? And we said that it is not necessary that Lagrangian has to be written in terms of the generalized coordinates all the time. It can be written in the Hamilton's principle or the distraction principle. It is formulated in such a way that it can be written in terms of any variables. Now, it may be that L doesn't depend on explicitly depend on the kth coordinate. Okay. In a particular case, particular choice of Lagrangian and coordinates, this may happen. This may even happen if so. This may even happen for when the number of degrees of freedom. So you are working with generalized coordinates also. So we'll come to examples of that. So what happens if this is? So this essentially means the mathematical statement for that is del L del QK equals 0. But you see that your Euler-Lagrange equation, so Euler-Lagrange equation tells you along the trajectory ddt of del L del QK dot is equals del L del QK, which is equals to 0 if it doesn't depend on the kth coordinate. Lagrangian doesn't depend on the kth coordinate, which means that ddt of del L del QK is 0, del L del QK dot, sorry. Del L del QK dot is nothing but pk dot. So this implies pk is a constant of motion, constant along the trajectory. Okay. So such coordinates are called absent cyclic, ignorable, or velocity coordinates. Chaosthetic essentially means velocity. Why it is called absent coordinate? Probably you have already understood that that coordinate is absent in the expression of the Lagrangian. That's why it's absent coordinate. I'll not tell you why it is called cyclic coordinate, so you can try to figure it out. If you figure it out, then you will understand part of how you integrate the Euler-Lagrange equations. But let me not tell you why it is cyclic here right now. As I said, I'll tell you part of the answers. Now, if pk is a constant, and say that constant is called some c or ck, then that gives me a differential equation. That gives me a differential equation which is only first order. How? Well, remember that L has a kinetic term which depends on qk dot square, or you can have like qk, qj type of terms, qk dot, qj dot, but it depends on velocity square. Well, obviously, if you are writing in arbitrary coordinate system, there will be the metric sitting at these places, but I am not. I'm just trying to make the point that it is still have velocity square, the kinetic terms. Okay, so if L has this, then del L del QK dot is linear in velocity, linear in QK dot. I should not say velocity because it's not velocity. It's a linear in QK dot, which means, which is nothing but that is pk. So which means that qk dot is a first order differential. So I will get something times qk dot or something times qj dot. So that type of equals ck. So this is only first order. So for the cyclic coordinates, the differential equation I have to solve for the trajectory of that coordinate. I don't need to solve the Euler-Lagrange equation, which is a second order differential equation, but I can solve a first order equation for the cyclic coordinate. and that will give me the trajectory for that coordinate, or how that coordinate changes with time. That's why it's called ignorable, because you can ignore one of the dimension. And you can see now again also why it is called velocity, because you are just solving that velocity equation instead of a quote unquote acceleration equation, which is the Euler Lagrangian equation is. The Euler Lagrange equation is like the rate of change of acceleration or rate of change of momentum, ddt of the canonical momentum. This must be the force if you compare it with Newton's law, del L del QK. Okay, so this is what is we mean by cyclic coordinate. So if there is a coordinate which is absent in the Lagrangian, corresponding to that coordinate you have a canonical momentum that is conserved, so that coordinate is called a cyclic coordinate. Okay, now it may seem to you that let me have a system. It may seem that I have a system and then I have certain constant forces, so it can reduce some coordinates. But I was lazy. I wrote down the Lagrangian in a coordinate system which doesn't take care of the constant forces. Because of that, I am getting back the cyclic coordinates. But that is not true because of this following statement. Let me make the statement and then explain to you why that the previous consideration is not true. Okay, so I mean to say right now that the cyclic coordinates not necessarily reduce the degrees of freedom of the system. Okay, for example, so let me give you a concrete example, a very simple example, free particle. So single free particle, one free particle. What is the Lagrangian? Lagrangian is just half m x dot square. If m is the mass of that particle, I have only one. So half m x dot square, if you wish, y dot square plus z dot square, right? And that's all the Lagrangian has, because it's a free particle, there is no potential. This free particle is absolutely free to move in any direction, but you still see that L doesn't depend on x, y, or z. So all x, y, z cyclic and this implies that px, py, and pz constant. That we already know, that's Newton's laws tells you that Newton's second law tells you that that should be the case, because it's a free particle, no force acting on it, its momentum should not change. Rate of change of momentum is 0. No force is acting on it, right? And we will look at the example of the central force, and you will see that there are several things which are constant, and for some of them you can figure out a cyclic coordinate also, which just comes out as the solution of the problem. The particle may or may not be restricted to move in all the directions. If it is restricted, then you reduce its degrees of freedom. But in this case, you can see the free particle is absolutely free to move in all directions. So degrees of freedom in this particular case is still 3, but you have 3 coordinates which are cyclic. Okay, so now if I have a cyclic coordinate, so let me discuss this thing called Route's prescription. which is to find a reduced Lagrangian when you have cyclic coordinates. And this will explain with an example. The example is one particle, three-dimensional motion, one cyclic coordinate. So I call these coordinates as x1, x2, x3, and the cyclic one is x3. Okay. So what do we want to do? So let us say that the Lagrangian. So this is, I'm writing down the Lagrangian in the most general form possible. Okay. So I will have the G's, and then I will have x1 dot, xi xj square. Okay. We assume that the mass of the particle is 1, or it is already included in G. This is the kinetic energy term, and the potential energy term. It can depend on all x1, these quantities. It cannot depend on x3 because that is cyclic. So remember, what are these? So these are, I have a summation over I, I also have a summation over j. So gij x1 dot square, I'm sorry, so these should not have the squares. The square is the multiplication of these two. So I can have gij x1 dot square, x2 dot square, then x1, x2, all these type of terms. Okay. Now, what is gij function of? Well, because the Lagrangian is cyclic, gij can only be a function of x1 and x2. It cannot be a function of x3. Remember that it is function of the coordinates, so it can be function of x1 and x2. So what is this? So this is the setup. First thing is identify the cyclic coordinate. So now I am coming to the prescription. Okay, so in this case it is x3. Calculate the momentum. Which obviously we'll call P3, corresponds to S3. So now what will be P3? Remember that this, let me write a few terms here. So this is G11, x1, x2, x1 dot square plus etc. Right? So then I can have terms like G13, x1, x2, x1 dot, x3 dot, etc. So if you calculate P3, then so there will be a x3 dot square term, so which will give me G33 x3 dot, and there will be terms which 1 and 3 which will give you x1 dot, and so please work this out by yourself once, so you'll get these terms. And this is, again, we are working in a general case. We will work this for the central force problem. Central force problem is a classic example where all these things come together. So we'll, once we go through it, we'll work out everything. So the prescription says that then solve. So this should be a constant, right? Let's call it C3. So then you solve for x3 dot in terms of. So x3 dot in this particular case will just become C3 minus G13 x1 dot minus G23 x2 dot divided by G33, right? So you may ask the question, what happens if G33 is 0? Okay, so think about it. What happens if G33 is 0? So I solve for x3 dot. Now what do I do? Now this is the step where this is something that you have done many times if you have worked with Lagrangian mechanics before, and this is the step where everything get it wrong. So what people do at this stage, and you should not do, is replace this x3 dot in the original Lagrangian. So the original Lagrangian, wherever I have x3 dot, they replace that x3 dot with this. That is wrong. So what you are supposed to do is this, this is the reduced Lagrangian. This is the one that you want to find out. And now this is a function of, that is the important thing, this is a function of x1, x2, x1 dot, x2 dot. There is no x3 dot in this, okay? And that's why it is reduced. So L minus, now this is crucial thing, C3 x3 dot. So I define L bar this way. Now I will not do the replacement because it will take quite some time to work it out. So what I will do is, I have the solution here and I will write down the final form of the solution. Again, it will be your homework to work it out. So this can be written in terms of half of G11 prime x1 dot square plus G22 prime x2 dot square plus 2 G12 prime x1 dot x2 dot. You see that this is my entire kinetic term which doesn't have any x3 dot term, and then minus, I will get an effective potential just like the reduced Lagrangian. This will be a function of x1, x2, x1 dot and x2 dot. Okay, so I don't want to write this V bar explicitly for you because that will actually, that's a little bit complicated expression, but you should work it out and see what you get. And this G11 primes, etc. So let me just write one of them. So this is G11 minus G31 square by G33. Okay, let me write G12 prime because that we will discuss a little bit. Is G12 minus G23 G31 by G33. Okay, so there's no harm in writing down the only thing which is remaining, and that you can figure out what is just looking at here. So this is G11, this is also 1 1, one with prime, the other with not prime, and then what I have written here is 3 with 1. So here I will write 2 with 1 and then G33. The reason I wrote all this down, these three expression, is there is a, so this is essentially the is the Raoult's prescription, and what it does is it not only changes the kinetic term, it also introduces an effective potential. And that potential can now include x1 dot and x2 dot, even if it was not there originally. Okay, so once you calculate v bars, you will understand that. Now, there is a special case which we can think of when in the original one, so all the cross terms, see, I not only have like x1 dot square, x2 dot square, x3 dot square here, I also have these terms in general, x1 dot, x3 dot. So if those terms are absent, which means that all gij for I not equals to j are 0, which makes g12, g31 and g23 all 0. Then you see this term goes away, this term goes away, and both of this term goes away. Then I just have g11 prime is same as g11, g22 prime is same as g22. And not only that, if plus, so this is a requirement on top of what we have already discussed, gij for I not equals to j equals to 0. If original velocity is, original potential is velocity independent, then the final potential v bar is also velocity independent. Okay, why do I come to this last point? Because this will be the case for the central force, so we'll see it there. Okay, so that is all that we had to discuss today. We discussed quite a bit of things today. We started by recapitulating what we learned last time about the Lagrangian mechanics, and we said about the special case where the Lagrangian doesn't depend on time explicitly, and we talked about the Beltrami identity. Then we moved into a little bit of discussion of calculus of variation, and we looked at two problems, both of were principle of least time, and I asked you to complete those two problems. And then we came to the discussion of the absent, cyclic, ignorable, or velocity variables. How a Lagrangian, if there is one coordinate absent in the Lagrangian, the corresponding momentum is conserved. And if that is the case, how you can use Routh's prescription to reduce the dimensionality of the Lagrangian, because that's obviously useful. And if you do that, it doesn't only change the kinetic term, but it also changes the potential term, so you get a effective potential. Okay, thank you. Please write your class notes and put the doubts in there.